Good afternoon and welcome to the 23rd annual exhibit of Hydrogen and Fuel Cell Technologies. We've been here for quite some time talking about research and development and commercialization. We have a specialist here to talk about a broad spectrum of issues, issues that are vital to the energy future of Germany, and I find it fascinating to talk about someone who's involved in computing the viability of all these different technologies and where they're going to come into play. I'll be talking to Markus Reuss, who's a researcher at Forschungszentrum Jülich. The booth is right over there. Please welcome with me Markus Reuss.
Hello, Brian.
Just in time for the hydrogen, the water. Of course, I forgot to mention the title of the topic, which is Linking the Power and Transport Sectors and Coupling It with Scenarios for Germany. First questions first, of course. Forschungszentrum Jülich, for those who do not know, what is it and what do you do there?
Yeah, so the Forschungszentrum Jülich is a big research center. It's belonging to the Helmholtz Association in Germany. And yeah, Jülich, perhaps a lot of people don't know where this is. It's between Cologne, Aachen, and Düsseldorf, so in North Rhine-Westphalia. And yeah, it's really a huge research center. We have around 5,000 employees there, and more than 50 different institutes working on energy and climate on one side, but we even having some some institutes working on brains and informatics by itself. Yeah, and I'm from one of these 50 institutes, the IAK3. It's the Institute of Energy and Climate Research, the Institute of Electrochemical Process Engineering, and yeah, there's our booth in some way, and our main field is fuel cells. So we started, I think, like 15 or 20 years ago with our research on fuel cell technologies. We have different departments working on normal PEM fuel cells or solid oxide fuel cells and on electrolysis too. I'm from a department working on systems analysis. So we think about, okay, how can we introduce and how can we use these technologies, these new technologies, in a future energy system?
And the issue is a pressing issue, relatively speaking, because we already have renewable energy. In Germany, they're shutting down wind turbines because the grid can't absorb the power. We have the North Sea as this immense resource, and there's a lot more energy to be won there. The only issue, and the typical German debate is, okay, the source of energy is in the north. How are you going to get it to the south? And there, through whose Bundesland are you going to have these huge cables running? Is it going to be in my backyard? So you have an interesting take on how to transport all of that energy from the north to the south. And I'd like to begin our discussion with that topic.
Okay, yeah, so we thought about, okay, how can we increase the renewable energy sources and the renewable energy power in Germany? Even if we have at some point, yeah, too much energy. So we modeled in some way an energy system in 2050, where we set up renewable energies in the size of like 170 gigawatts of onshore energy in onshore wind power plants in Germany, and 60 gigawatt of offshore wind energy. And we modeled this with actual weather data from the German Weather Institute, and we, in some way thought about, okay, how much power will they have as an output, and finally we found out then that on the one side we produce a lot of energy at times where we can't use it. So that means that even if I produce now, or even if I have now a lot of potential renewable energies, I can't use it anywhere in Germany. On the other side, we have a lot of energy that we are producing, but we are not able to transport it to the south. And therefore, we thought about producing hydrogen and transport this hydrogen via a hydrogen pipeline. Yeah. And with this pipeline, we don't think about using this hydrogen directly back in the power sector. We try to use this hydrogen then in the mobility sector and supplying with it the fuel cell electric vehicles in Germany.
So this is all, the take is, and here I want to get to the details because they're so interesting. The debate right now in Germany is framed, we're going to run cables. You know, all the way to the south of Germany, that's where the power is needed. Electrolysis is always an option, and in fact, it sounds like a great option sometimes if you can produce and then consume on site. You have that wonderful microsystem, you know, an independent, decentralized grid here. But you're talking about a massive quantity of energy. You have the cost of electrolysis, and then you have to think about how to get that, how efficiently to get that to the south. What makes the addition of electrolysis in the pipeline superior to electrical energy transportation? Is it simply that people don't like the cables in the air? Are the efficiencies greater? Is the applicability better? Does it add a storage factor? What are the advantages to doing that?
Yeah, so like you said, the one main option and one main benefit is that we having a storage option, really, a huge storage option. So we're talking for our scenario in the range of 3 million tons of hydrogen. This is in the range of like 150 terawatt hours of energy, and we are in the from today's perspective, we are not able to store this amount of energy without hydrogen. It's just not possible. And yeah.
So this, you know, the storage options are limited. I've had this conversation before. You could pump water up to the top of a mountain. There's not enough lakes up in the air to store the amount of energy potentially harvested from the North Sea, from the prevailing winds there. Okay, so you have this source of hydrogen simply because you're deciding not to keep it in electrical form. You get it to the south in a pipeline. I suppose two questions. One is there's an existing natural gas grid. People debate how much of the energy produced and converted to hydrogen through electrolysis, how much of that natural gas can go into the how much of the hydrogen can go into the natural gas grid, or do you want to keep it as pure natural gas, or as pure hydrogen, I'm really confused here, and transport that to the south? What is the benefit of having a pure hydrogen output in the south of Germany?
So the main benefit of the system is that if we produce this hydrogen for a very at high costs in some way, because the hydrogen we can't assume that, for example, the renewable energy that we use to produce this hydrogen is for free. We have to, give the wind energy supplier some money for the energy he's supplying, and therefore, if we're talking there about as a today normal onshore wind energy plant, it's already possible to operate it for something in the range of 6 cents per kilowatt hours. If I have then I don't have 100% efficiency for the electrolysis. We're talking about there's somewhere in the range of 70%. That means that we have to already sell our hydrogen or our energy later on for a higher price. And keeping it in pure form, we have then a hydrogen and an energy carrier that is very valuable. And by feeding it into the natural gas, it is from our perspective a waste of money in some way, because we're having a very high valuable energy carrier with a hydrogen, and we could use this high value energy carrier, for example, in fuel cells, and having there a higher efficiency than, for example, I can achieve if I burn this natural gas. And if I'm feeding it into the natural gas grid, I would have to burn it later on, because I can't use the fuel cell. Therefore, I would perhaps, if I have a reformer or something like that, it would be possible, but generally it wouldn't be possible.
And of course, once you have natural gas, you have these very efficient, rather sexy units called PEM cells that can turn it back into electrical energy. For me, it's fascinating. one has to think, if you want to expand the source of renewable energy, we're talking about wind turbines and solar, you have to provide those people who install those devices with a financial reward. They have to be profitable, okay? And talking to you, you mentioned one fascinating idea. I thought, okay, if you have hydrogen, what you do is you plug hydrogen in people's homes, and they can re-electrify that hydrogen, they can use it for their electrical energy, and you said immediately, no, no, no. Who's going to pay more for hydrogen? And you focus on one specific market, which is?
Yeah, the mobility sector. So basically we're at the actual state, we just focus on the mobility sector in our modeling. That means we want that the hydrogen is fueled into fuel cell electric vehicles, because the mobility sector is, we can reach their comparable high fuel costs in some way. The fuel costs, for example, for diesel pre-taxes in 2014 was around 8 cents per kilowatt hour. If I compare this value with the value I can achieve today, for example, with natural gas, I'm in a range of 3 cents per kilowatt hour. And if I then add this beneficial effect of the fuel cell that I have with the fuel cell, an efficiency of like 50 to 60% compared to the diesel engine, the internal combustion engine, which has like 20 to 25, I can have a higher cost for my fuel, but achieve the same distances in some way. That means that my mobility by itself is much cheaper. And the advantage is that we are competitive. If we consider all of these costs together, we showed in our energy system that the hydrogen is a competitive energy carrier for the future in the mobility sector. And yeah.
So that basically it's the most profitable way to market this hydrogen. I find it a fascinating argument. The purists would like to see that perfect system, hydrogen production through renewable energy, then you plug it back into a PEM cell, you get the electrical energy back. There's another option, though, which is methanization. People love this because, of course, the natural gas grid network in Germany particularly could be also a huge storage facility. That is, if you use the hydrogen you create, methanize it, you have this immense grid, you can put terawatts, gigawatts of renewable energy into that grid. You're not a big fan of methanization.
Yeah, for the methanization, it's in some way the same problem as we have if you're just feeding it in, or feeding the hydrogen into the natural gas grid. Because the methanization by itself adds additional costs to the kilowatt hour in some way. And finally, we're still having just natural gas. And the natural gas is, today, if we just see, okay, natural gas has a price of something like 3 or 4 cents per kilowatt hour. And we won't be competitive to this. And if you just think about, okay, who would use these amounts of natural gas that we are using today if the price is not like 3 or 4 cents per kilowatt hour, but it's in the range of 10 or 12 cents per kilowatt hour. It's like the double or 3 times the price that we have today, and then it's not anymore a business case, perhaps. No one knows this, but from today's perspective, it's not really useful.
It's not really useful. I should add, if there's any questions from the audience, just raise your hand and we'll try to address them. The issue of what comes next, I find complicated because you've confronted me with a few added reflections. If I can go back to the fundamentals, the modeling you do is based on the presumption that there are already significant quantities of renewable energy. The next step is to assume that the expansion of the production of renewable energy is not going to depend on goodwill and tree huggers like me. It's going to depend on financial viability. Okay? So that assumption is okay. The next stage, though, in all of these reflections could change if you enter into the field of energy self-sufficiency. All of the natural gas that you allude to as a competitive price factor against which the fuel cell industry in hydrogen has to compete is a foreign input contingent upon a stable international environment and so on. So are you ever forced to factor in other aspects that could change? Or are you more focused on this is the current prognosis? That is the current situation. You can already say, we can't store enough of the energy, the renewable energy now. This is where we have to fix things. And under present circumstances, these are the options we have. So do you do future prognosis, or do you look at the realities?
Yeah, so we make, at the moment, most of the time, future prognosis. So that means we are looking for this energy system 2050. We're having there certain boundaries, for example, this 80 to 95% emission reduction goal from the German government. But nevertheless, the one point that you just mentioned, this energy self-sufficiency in some way. This is even another point we could address with the hydrogen. So you said about the storage options, or that this is a foreign input. In all of our analyses, we try to implement huge storage amounts as an energy reserve in some way. That we are not just focusing on saying, yeah, we're making for once the optimal system, which is in the reality would never work like that. Because even today we're having huge storage capacities of natural gas for a strategic reserve. We always assume that we have in the future the same amounts, and we have to store and we have to supply this storage reserve in some way.
So the assumption, though, is that the energy market is not volatile, generally speaking.
Yeah, at the moment. Yeah, for the future, we're trying to address these issues, that we're having not already a perfect system, but we don't having all of the today's regulations for the future. That means that we still need a change. And at the moment, I'm talking about this energy system 2050 as a potential case for the future. Nevertheless, there are other issues we have to address. So we can say now, okay, in 2050, this energy system would be, as a greenfield, the optimal solution for everything. But nevertheless, we're having today already an energy system, and how we make the transition from today's energy system to the future. This is another aspect we have to address, and we have to focus on. So from today's perspective, you would say, for example, okay, how can I get the most reduction in CO2 emissions for the next 5 years? As we have it now, the problem that we set fixed targets for 2020. And we don't achieve this, I would say, if we build now completely everything with fuel cells tomorrow, and we don't have the renewable energies on the one side, we don't have the demand, we don't have the infrastructure for it, and it has to be a transition phase in some way. And this transition phase is one of the other aspects we are trying to focus in our research.
I hope everyone was listening carefully, because I heard a tree hugger hidden behind the transition phase. Every 100% renewable energy economy is energy self-sufficiency, it seems to me. The end goal, where you arrive, is using sustainable resources largely produced locally, and that is the end goal. Nevertheless. It's always fascinating to me. We arrive at the same destination. It's only the question about how we're going to get there. This has been a fascinating topic for me. I've learned so much. I encourage you all to visit the booth there. They're specialists in transitional technologies, and they're specialists in looking about how we're going to get to the 100% zero emission future we all hope someday will we'll survive to see. Thank you very much, Markus. Markus Reuss from Forschungszentrum Jülich. Hope I see you back here next year.
Thank you.
Thank you. And thank you. We'll be returning in just a few minutes to talk to Brian Cheadle, who's Director of the Global Business Development at Dana Incorporated. It's always a pleasure to have you here, sir. And we'll be talking about supply chain participation in the move to electrification and fuel cell and battery components. So stay tuned, have a drink there on the house.